My name is Maria Bondesson. I'm an associate professor at the Intelligent Systems Engineering Department. The problem that my research group works on is the problem of environmental pollution. There are more than 80,000 industrial and agricultural chemicals on the US market, and hundreds of new chemicals are produced every year. In classical toxicology, you test the toxicity of compounds in rabbits or in rodents. And this is both time-consuming and expensive. And this has in turn led to a huge backlog in toxicity testing. And only a small fraction of all environmental pollutants have been fully evaluated for human health effects and for environmental effects. And I'm particularly interested in the developing embryo, and there's not much information on the effects on developing embryos. And we are all exposed to a mixture of compounds, but mixtures are rarely at all tested in toxicity testing. So we need a new strategy to meet these challenges. And in my lab, we use zebrafish as a toxicity model. We think zebrafish is good because it's an animal model, an in vivo model. From each single pair of adult zebrafish, we can produce hundreds of embryos in a mating. The embryos are small and transparent, and they have a very fast embryonic development. This embryonic development is driven by molecular mechanisms that are similar to those of higher vertebrates. There is also an availability of transgenic fish that has fluorescence in specific tissues and organs. And that means that we can study and see these tissues and organs. So we can, for example, see the blood vessels, the fish yolk, the sensory neurons, the motor neurons, and the muscles. Zebrafish is also good because it's amenable to high throughput screening. So we can put hundreds of adult fish in the so-called mass breeder. We obtain thousands of embryos, which we put in 96 well plates. And then we use a robot to add different chemicals to these embryos. We incubate them, we put them through automated imaging, and then we get the images, and the images are analyzed by image analysis, or in some cases, machine learning-based methods. So therefore, we can obtain a lot of toxicity data fast for a lot of chemicals. And then we compare our data to a large database of information on toxic chemicals. And this database is produced by the TOX21 consortium, and it has a lot of mechanistic information on how toxic chemical works. And then from there, we can find other chemicals that work through the same mechanisms. I'm going to show you one example. We screened about 300 chemicals for skeletal disruption. We used a transgenic fish that has fluorescence in the bone, and particularly in one thin bone called the clatrum. And we identified 38 skeletal disruptors that perturb either the length or the structure of the clatrum. Then by comparing our information to the database, we could find that vitamin D3 metabolism was often altered by chemicals that perturb the skeleton. And therefore, we can go in zebrafish, do the verification, and we can rescue the effect by adding back vitamin D3. And then we have less of skeletal perturbations. And it is known since a long time that vitamin D is very important for human skeletal development. And if you don't have it, you will have severe deficiencies or malformations of your bones. Then we can extract the new chemicals that also act through the same mechanisms. And we can go back to the zebrafish model and test if these chemicals indeed perturb skeletal disruption in this case. And here we tested 6 new chemicals, and they were all skeletal disruptors. So in summary, we identify through high throughput screening new chemicals that are toxic for a specific endpoint. We extract the mechanisms through correlations to a database. We can identify or predict new chemicals that act through the same mechanism. And this is done at a much faster speed than traditional toxicity testing. And our goal is to replace the current toxic chemicals with new, safer ones. The work I presented was done by two of my graduate students that are still at University of Houston, Savina and Rajna, in collaboration with Cliff Stefan and his group at the high throughput screening facility at Texas A&M. And the correlation studies were done together with Richard Judson at the National Center for Computational Toxicology at VA. Thank you.